Good morning everyone, I am Renu Sharma, Assistant Professor EC Department. Today I am going to start with the next lecture of Unit 2. Now this lecture is related to some of the numericals for FM and PM, the concept of which we have discussed in the yesterday's lecture. So this is an example of related to FM and PM. VHF, that is very high frequency, or FM wave is there, having frequency band of 30 megahertz to 300 megahertz radio transmission. Now in the band of 88 megahertz to 108 megahertz have the following parameters. So these are some of the parameters. These are basically standard parameters that you have to consider while solving any numerical related to FM. So the maximum frequency input is FM is equals to 15 kilohertz. Its deviation, that is delta FC, is equals to 75 kilohertz. Then modulation index, that is beta. So in the standard form, the modulation index is related to, or it can be shown by a parameter, that is beta. So here beta will be is equals to 5. So these are the standard parameters related to the FM signal. So beta formula will be delta FC upon FM. For beta is equals to 5, there are 16 sidebands and the FM signal bandwidth is 16 FM is equals to 16 into 15 kilohertz, and which is equivalent to 240 kilohertz. So after applying the Carson's rule, now this Carson's rule is very famous formula for bandwidth calculation of FM signal. Now its value will be twice of delta F plus FM. Now if you want to reduce it to modulation index, then its formula can also be written as 2 FM MF plus 1. Now MF can be replaced by beta also. So this is modulation index plus 1 multiplied by 2 FM. So this is the Carson's rule for bandwidth calculation. Now this is the spectrum that you can plot, whose bandwidth is 16 into FM, which will be equals to 16 into 15 kilohertz, because this is the bandwidth of the input signal, 15 kilohertz. So this is the spectrum that you can draw for this particular condition. Now next is some of the comments related to this particular numerical. Like the FM spectrum contains a carrier component and an infinite number of sidebands at frequency FC is equals FC plus minus n FM, where n will be from 0, 1 to up to infinite. So this can also be reduced to Bessel function, or Bessel function of nth order and first kind. So it will be written as VST is equals to VC, summation n is from minus infinity to infinity, Gn beta cos omega c plus n omega m t. Now in the FM we refer these sideband pairs, not the upper and the lower sideband pair. Carrier or other components may be suppressed in the case of FM. So there are basically two cases, NBFM and WBFM. In case of NBFM, that is the narrowband FM, where MF is far less than 1. In that case only two sidebands exist, that is upper sideband and lower sideband. But the case where MF is far greater than 1, like in case of wideband FM, there are infinite number of sidebands which will exist. Now these infinite number of sidebands can be shown by this Bessel function. The relative amplitude of components in the FM depend on the values, that is G and beta, where beta is equals to alpha Vm upon FM. Thus the component are the carrier frequencies depends on MT, as do all the other components, and none may be suppressed. So this is related to G and beta. Components are significant if G and beta is far greater than equals to 0.01. Now there are two conditions. For NBFM, beta should be less than 1. For beta, when beta is greater than 1, it will be WBFM. So G and beta, when it is greater than less than 1, or it can be taken as 0.3 also, only J0 beta and J1 beta will be significant. So only the carrier and two sidebands will be present. So bandwidth is 2 FM in the this case, and that is equivalent to a DSP AM, that is double sideband amplitude modulation. Now next will be the large modulation index for the large value of modulation, that is beta. Its value is beta is equals to delta fc upon fm, means that the large bandwidth is required. So in that case it is known as wideband FM. Now the FM process is basically non-linear in nature. The principle of superposition does not apply over here. When empty is a band of signals, example speech or music, the analysis is very difficult, means it is simply impossible. If we are considering a speech signal or music signal which is continuously varying in time, and that is the example of one first dimensional modulation. So calculation usually assumes a single tone frequency equal to maximum input frequency. Example of this will be 20 kilohertz, that can also be written 20 hertz, and after modulation its value is 15 kilohertz. So FM will be 15 kilohertz, which will be used in this particular case. Now next is the example that is related to the NBFM, narrow bandwidth narrow band frequency modulation. Now its beta is equals to 0.2. So this is less than 0.3, also this is less than 1. Let Vc is equals to 10 volts. The total power in the infinite spectrum, that is Vc square upon 2, is equals to 50 watts. So that can also be written as summation n is from minus a to a, Jn beta square is equals to 50 watts. So that will be equivalent to Vc square by 2. So from this table the significant components are, let's say in case of NBFM there is only J0 beta and J1 beta exist. So this is what it is written over here for n is equals to 0 and n is equals to 1. Now Jn beta, beta is 0.2. So for this particular case its value will be this one. Now amplitude we have to calculate. So Vc into Jn 0.2, which is equals to 9.90 or 0.995. Then power will be is equals to amplitude square divided by 2. So after solving this we will get the power, that is 49.5 watts. So the carrier plus 2 sidebands contains 49.5 divided by 50, which is equals to 99% of the total power. So this is the case of NBFM. Now next is the distortion, how we have to calculate the distortion of the particular signal. So distortion formula is total power minus PBL divided by PT, which is equals to 50 minus 49.5 upon 50. So this is equivalent to 1%. So actually we don't need to know the value of Vc, that is alternatively we can also find it directly using this particular formula, that is distortion is equals to 1 minus summation n is from minus 1 to 1 Jn beta square, where beta is 0.2 that we have considered in the numerical, and n will vary from minus 1 to plus 1. So there are basically 3 values, that is n is equals to minus 1, n is equals to 0 and n is equals to plus 1. Now d will be equals to this value and this value, which is equals to 0.01. So ratio will be equals to P power in BL divided by total power, which is equals to summation n is from minus 1 to 1 Jn beta whole square. So this will be the final value, that is 0.99. Now next will be the FM demodulation. Now what is FM demodulation? We have discussed in the earlier lecture about FM modulation. So in case of this FM demodulation of or the frequency discriminator, it is essentially a frequency to voltage converter, and frequency to voltage converter may be realized in several ways, including for example tuned circuit, it can be realized, an example envelope detector, phase lock loop, that is PLL. So demodulators are also called as FM discriminators. So before considering some specific types, the general concept of FM demodulation will be presented over here. And frequency to voltage converter produces an output voltage, that is V output. So this is basically the block of frequency to voltage converter. Here input frequency is given by Fin. So the output frequency, that is voltage, output will be the voltage, because it is a frequency to voltage converter. Whatever frequency we have applied at the input, it will be converted into corresponding output. So that is denoted by V out. So this is given by this particular equation. Now next is, if the input is FM, the output is MT, the analog message signal. So if the input is FSK, the output will be DT, the digital data sequence. So this is what it is showing in terms of analog modulation and digital modulation. So in this case, Fin is the independent variable and V naught is the dependent variable, x and y axis respectively. So the ideal characteristics is shown over here. As you can see that this is V output versus Fin graph, because this is frequency to voltage converter. So input will be the frequency, output will be the V output. So this is what it will be shown over here. This is the center frequency, that is Fc, and corresponding to that we are getting the value of V naught. So this is the graph. So we define V naught as the output when Fin is equals to Fc, the nominal input frequency. So the gradient delta V upon delta F is known as the voltage conversion factor, that is related to frequency to voltage converter. That is, gradient is equals to voltage conversion factor, or K volts per hertz. So considering the slope of this particular equation, that y is equals to mx plus c, etc., then we may say V out is equals to V naught plus K into Fin from the frequency modulator. And since this V naught is equals to V out when Fin is equals to Fc, then we may also write this particular equation, that is V out is equals to V naught plus K alpha into V in. This is nothing, this is the proportionality constant, where V naught represents a DC offset in V out. So this DC offset may be removed by level shifting or AC coupling. So this is the working of the frequency to voltage converter. Now next is this slope, this particular graph which is been drawn again between output voltage versus input frequency. Now you can see that this is the input center frequency, that is denoted by Fc. This is negative deviation, this is positive deviation. So the important point is that V output is equals to K alpha into V in. Now if we consider V in as empty, that is the message signal, then the output contains the message empty and the FM signal has been demodulated. So basically what we need to say, what we are trying to say, that in case of frequency to voltage converter, input will be the frequency and output will be the voltage, and if input voltage is considered as the message signal, then it is easy to demodulate the particular signal. Now next is, often but not always, a system designed so that K will be equals to 1 upon alpha. So whatever constant we are considering, this is nothing but the proportionality constant K into alpha. Now if somehow we consider it as 1 upon alpha, so this will be equivalent to 1. So V output will be equals to V input. So this is the main aim, so that K alpha is equals to 1 and V output is equals to empty. So a complete system can be shown over here. In case of this voltage, first we have to use voltage to frequency converter, then we are using frequency to voltage converter. So in case of voltage to frequency converter, input will be the voltage, output will be the frequency. Corresponding to that, there is a gradient, that is alpha hertz per volt, that can also be written as Kf. Now Kf is what? It is frequency sensitivity, that is related to the FM modulator. Now alpha is frequency conversion factor of frequency sensitivity. So F out in this case, the equation will become Fc plus alpha into V in, or that will be equivalent to F in. Same, when we replace this V in by MT, then F out will always be is equals to F in. Now since we want to work it as a demodulator, the output of the final demodulator should be a voltage. So we have to use a frequency to voltage converter again. Now next, for this the gradient will be K hertz per volt. K is voltage conversion factor. V output will be equals to V naught plus K alpha into V in, and this will be is equals to V naught plus K alpha into MT. So that is the case of output voltage. Now next is this one, which is showing the S curve. This one, this is basically showing the change in the carrier frequency to the positive side and to the negative side, that is known as the frequency deviation, positive frequency deviation or negative frequency deviation. So in this case, as you can see that this is the F output, this is the center frequency. Corresponding to that, there is a graph has been drawn, and this is how the carrier swing will be there. Means carrier swing, this will be the center frequency, it will be to the positive side and it will be move to the negative side. So this will be delta FC and this will be minus delta FC. This is negative part, that will be positive part. So this is related to the frequency, this is related to voltage, that is positive voltage variation, this is negative voltage variation, this will be the reference value. Now next is FM demodulator 1. So this is the first type of FM demodulator. So this is tuned circuit. One method is to use the slope of the tuned circuit in addition in conjunction with the envelope detector. So this is the diagram of the envelope detector, where there is a diode and capacitance and inductance is connected in parallel as a load. So that will be acting as a tuned circuit, that is tuned to center frequency FC. Now this will be the FM input. Now after passing this FM input to this particular tuned circuit, again there is a tuned circuit, this output will be somewhat like this, and then this will be the output. Now after passing through this envelope detector, the demodulated output will be somewhat like this. So this is similar to what we have modulated. This is the explanation of the first demodulator. The tuned circuit is tuned, so the FC, the nominal input frequency, is on the slope, not at the center of the tuned circuit. This is what, this is at the slope side, not at the center of the circuit. So as the FM signal deviates from about FC on the tuned circuit slope, the amplitude of the output varies in proportion to the deviation of FC. So same what we have done in the modulation side, where center frequency is FC and it will either move towards positive side or towards the negative side depending on the amplitude of the message signal, whether it is varying positive side or to the negative side. So same is done with this demodulator in the FM case. Note, in the early days, most radio links were AM, that is DSP AM. When FM came along with its advantage, the link could be changed to FM quickly. So hence NBFM was used, the carrier frequency FC was chosen, and the IF filter, that is intermediate frequency filters, were tuned so that the FC fell on the slope. So basically, when we have moved from AM to FM receivers for the demodulation of the FM signal, then super heterodyne receivers are used. So whatever incoming radio frequency we are having, it will be changed to a IF frequency, that is known as intermediate frequency. So according to that, there are different filters are used. So a better method is to use two similar circuits, that is known as Foster-Seeley discriminator. That is very important kind of discriminator that we are seeing. So this is the demodulator. So to the demodulator, the input will be an FM signal. Now the upper half of this particular circuit, as you can see, this is tuned to frequency F1 and the lower half is tuned to frequency F2. This secondary winding is center tapped transformer. So there are two different capacitors which are used, then two diodes are used over here, and again there is a tuned circuit which is a combination of L and C. So this gives the composite characteristics which is shown over here. D2 effectively inverse the F2. tuned response. So this gives the characteristics S type of detector. So this is nothing what I have told you. This is S curve. Now next is another type of demodulator is phased lock loop. Phase lock loop, that is PLL. In short, it is known as PLL. Now PLL is a closed loop system which may be used for FM demodulation. A full analytical description is outside the scope of this particular description. What we are doing over here in PLL, there are three basic elements of a PLL. First one is the error detector. This is a error detector. Second element is low pass filter. Third element is voltage controlled oscillator. So this is known as VCO. So the input to this error detector, this is known as FN, that is input frequency. The output will be either the summation or it will be the subtraction of the two input frequencies, which means it can be FN plus minus F naught. The output of this will be applied to the low pass filter. Then in the feedback, using the voltage controlled oscillator, what we have to do, it has to lock at a particular frequency, that is at the set frequency, that is known at PLL. So note the similarity with a synchronous demodulator. The loop comprises a multiplier, low pass filter and VCO. So these are the three important components of the PLL. Now this is the description. The input is applied to the multiplier and multiplied with the VCO frequency output to produce summation Fin is equals to Fin plus F naught, or it can be the subtraction, that is Fin minus F naught. Now the low pass filter passes only Fin minus F naught to give the V out, which is being proportional to Fin minus F naught. So basically the output of the error detector or the subtractor should be equivalent to 0. So we have to set the frequency like that only. So if Fin is equals to F naught but not equal, it is a low frequency signal to the VCO. This signal V in causes the VCO output frequency F naught to vary and move towards F in. So this is the description of the corresponding PLL. So today's lecture we have discussed about PLL and different types of FM demodulator. Thank you.